It is so obnoxiously loud when he tells you it's recording. Okay. All right. Share. I feel like it's always shouting at me. Sent. Am I in the right week? We'll find out in a minute. All right. You can see my screen? Perfect. Wonderful. Okay, so week 5, power, which we thought we had scared everyone away, but apparently not. So let's make sure I'm in the right slides. Yay. Perfect. It's been that kind of Thursday. So I'm going to briefly cover what is a power analysis. I know that many people already know, but just kind of give you that background and then talk about some considerations and then do a little demo of G-Power and the Power package. And then we'll talk about what can happen next week since we have an open week. So we'll do our brief overview of Power. It's not really a BTS Power overview, but more like here's some packages and software that you can use, and then questions. And I did look up latent profile Power stuff actually for you this week. I'm afraid my answer isn't great, but I did look things up. So in general, the purpose and usefulness of power analyses is to help determine the sample size required for a study. So there are many components that kind of integrate together to ultimately affect the decision that we make, especially in frequentist statistics when we use p-values. Obviously, Bayesian statistics are also influenced by different components of power. So the main pieces to the puzzle are effect size. We don't necessarily always have control over effect size, so it's something that just sort of make your best guess on the low end so that you can overpower your study given what we know about the sort of file drawer problem and reproducibility. Effect size, sample size. This is the one we have the most control over. So I think that's why most people focus on it for estimating a priori before a study. So effect size, sample size, type of test. So the test/design, some tests are more sensitive, so they have more power. We talked last week about multi-level models having larger power than other types of designs because they increase the degrees of freedom, and the degrees of freedom directly tied to sample size, which then increases overall power. So those are kind of the main big components to power, and the control that you have normally is tied to sample size and or research design. But some studies may not have the ability to manipulate research design to a repeated measure study because it's not ethical. So most people focus on sample size because it's the thing we have the most control over when it comes to planning, right? You may not have control in the sense of like, I don't have the money, but, and so it helps us understand the likelihood of detecting effect if there is one, right? So the big caveat when it comes to power is that this is the likelihood of finding that effect if it truly exists, right? So if the null hypothesis is true, no amount of power will help. Then it ensures the, oh, this is a repeat, sorry, thought I took this out, but ensures the study has the sufficient sample, right? And in theory, it helps us avoid wasting resources. So underpowered studies are not desirable because they may or may not tell us what we actually want to know. There is a current trend about thinking about how big team science studies may be a waste of resources on the other end, like that we're oversampling, or you know, at some point we should be able to stop and say this is good enough. It is a toss-up. Obviously, I prefer to overpower than to underpower because underpowered studies may not tell me anything, whereas overpowered studies at least tell me something. So I would say the goal is to find the sweet spot of an accurately well-measured phenomenon, right? So finding that spot where you've got enough power, and if you go over it, great, but maybe not so much that we're wasting our money by collecting more data points when we know the answer already. So there are some folks out there who say that these are big team studies are sometimes a waste of resources the other way. Okay. Are the slides possessed or is it just me? Okay, maybe messed up the slides last night. It was late, but we'll fix it. Okay. All right, two main types of power analyses, and we can talk about both. There are other types of power analyses, but those other ones, Savannah had a very cute picture in here. They're crap, so I didn't want to talk about them. A priori power analysis, which is hopefully the desirable goal. This means before the study begins, or before data collection, or before running the analysis. So if you're like running, collecting data, trying to figure out when to stop. So it helps us determine that necessary sample size for a given set of power, effect size, alpha level, and research design. So this is where I'm going to say my caveat that all power analyses are wrong and some are useful. Okay. Meaning that if any one of those components that you change the statistical test, that power analysis has nothing now to do with what the results you're going to see. Many statistical tests have the same sensitivity. So there is a measure in more math stats of how sensitive a test is to detecting the known effect, right, with simulation studies. This is where that whole like assumptions thing comes in. So if you don't meet the normal distribution assumption and you have a smaller sample size, non-parametric tests are more sensitive, okay, to the same effect. Where was I going with this? Right. So if we change any one of these pieces, obviously the power changes. Most of the time we don't change alpha. Most of the time we don't change the set power that we would like 80% is a very popular number in social sciences. It's usually the effect size that's wrong. That's why I tell people to estimate lower. But once you get over the fact that all power analyses are wrong, it's helpful to realize that you're just doing your best guess here. And I think reviewers sometimes are a little too mean on power analyses. Like when I'm reviewing something, I look for, did you give me enough information in your description of your power analysis that I could reasonably come up with the same number? So people will tell me they use G-Power. Awesome, great free software. I really love it. But then they'll say that we did with an ANOVA. Okay, well, what are all the numbers that you put in the boxes so that I can actually click it myself? So I think we still have a long way to go. If you're going to use one of these pieces I'm going to show you today, just include a screenshot in the supplement. Can't hurt. Because then later, if we use that analysis, we can remember what we did. Because that happens a lot where you can't quite remember exactly what you came up with. So it's hard to justify or explain later, right? And so our goals for when it comes to submitting for us is to just get an idea of what the resources you need are. So on the PSA side, reviewing these proposals, large components about feasibility. And so that's why the power analysis becomes important. So how many people do you need, and can we collect enough labs for that to be a reasonable number? All right, the other thing that you can do is sensitivity tests. I really love sensitivity tests. Sometimes people conflate these with robustness tests. I think they probably can be interchangeably used depending on the context. But the idea is like, what is the effect size that I could find if I know that my sample size is fixed, right? So we often do these at the end when, especially if the result comes out null. I say, okay, well, given our sample size and, power, alpha, blah, 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 here's the effect we could have detected if it existed. So this often helps us justify that the effect we could have detected was not like 200 and we only got 4 or something, right? So like it allows us to be like, this effect just really isn't there because we could have detected a really small one, but it's just not there. So these are pretty handy at the end. Okay. There are other types of power analyses that you'll see people talk about a posteriori, meaning after the fact. There's a lot of controversy over power analyses at the end of a study. Like, I've always heard that they're bad, don't do them. But there's kind of a history there where people were trying to justify that their sample size was large enough to detect whatever. I would say sensitivity analysis better fits that goal of like, here's what I could have detected with this study, right? And if the only thing you could have detected was a super large effect size, then the study is underpowered. So that to me kind of helps with that. What could I have found? And then there's even more that I was like, what is this even thing on this wheel picture that Savannah had in there? And I would say they're just not very common in social science. So it's usually these two, although you might see sensitivity called robustness. But people often use robustness to mean like it's robust to other added covariates, or it's robust to other, these other manipulations. So I tend to say, if you're just saying, what is my minimum sample size? It's a sensitivity analysis. Okay, but the terms get conflated. Okay, so that brief aside and the slide hiccups, how does this work, right? So we have to define our research hypothesis. These are steps we've already taken in our workshops here. So defining what we're testing, because that helps us figure out the analysis that we're using. What is my effect size? So prior research, pilot study, domain knowledge, or the smallest effect size that you would reasonably be interested in. Okay. And that can be very, very hard to define, as we've talked about in previous weeks. But anything that you pull from the research, I might tell you to calculate the lower confidence interval of it and use the lower end, which I'm happy to help you do. I have also some point and click software that's an R package that would allow you to do that by filling in some cells. It's called Moat. And that is a more reasonable estimate using the lower end confidence interval than using the raw effect size, because of things that we know about publication, right? That the raw effect size is probably too large. Okay. You could also just say, I'm going to half it, because that's what the Open Science Collaboration showed. And I would say, great, wonderful. Okay. The wild thing to me about these effect sizes is it really is so field specific. So if you're doing like perception research, their effect sizes are like 3, and that's normal as a Cohen's d, which is a z-score, and 3 is like wild. I'm like, really? And then they're like, we're going to test 4 people. And I'm like, really? But it's super normal in that field, because they are manipulating the study to find that effect size being that large in a sense. There's a lot more control there. Whereas when I work with my clinical friends, we're like super hoping for like an R squared of 0.02, right? So it's sometimes very hard to help people come up with their smallest effect size of interest, but I'm happy to kick around ideas. Choose a significance level. I feel like I should say justify your alpha, because I was on that paper, but I'm also bad at this. 0.05 makes me happy. It's my favorite number. So, I think you could say your justification could be because it's normal. It's the common field. It's the right balance of type 1 error, right? Now, remember that type 1 error and power/beta are not related. Okay, I think, unfortunately, because places that do register reports have been asking for 90 and 95% power, that it's easy to conflate. Oh, if it's 5% alpha, it's 95% power. That is not, they're 2 separate components to the probability puzzle. It's beta that you're actually setting to usually 20%. So you're allowing yourself to make a type 2 error where you miss the effect 20% of the time, because we think that those are more acceptable, right? So it's better to miss the effect and say, well, we just didn't find anything. It could be there, than to say something's there and is not. So I always tell my students, the first mistake is the worst mistake, because you're making a claim that isn't actual. And then we talk about policing, because for some reason, type 1 and type 2 error fit really nicely into this, just thinking about detectives, right? So you want to make sure you have enough power to detect the effect that's there. So enough evidence to convict, right? And you don't want to make a type 1 error and send someone to jail when there wasn't enough evidence there to convict. And so kind of nicely maps onto this whole criminal justice system concept. Maybe not practically, as both are implemented, right? But So we being social scientists, typically set this at 80%. And this is based on a long history of fights between old statistician dudes, where it just seems like 20% miss rate is okay, but you can set it higher. If you want to set it to 90%, I will tell you, if you're thinking like, maybe I want to submit to a registered report to Nature Human Behavior, that they're going to ask you for 95%. So you might consider that choice just because that's what they're going to ask for. And then do the analysis, right? So one step here that's sort of missing that I think I missed last night is that you have to know what the design is. So what statistical analysis are you running? Because that will change how you calculate the sample size. All right, so I'm going to show you both GPower, which is really great if you are like the typical design is an ANOVA, right? So we talked about this, I think, last week and maybe before. If you aren't sure how to scale up the analyses, like you're like, I have never done an MLM and I don't want to even mention this word, you could say the typical design is this analysis, and we're happy to take help scaling that up based on the admin team. Like, we don't expect you to know how to do everything. That's useful information, and then calculate the power based on that. Okay. Because that gives us a good feel for feasibility. So how many participants would you need in each country or each language, et cetera. So for simpler designs, I suggest GPower because it's fairly simple. And then just a light bit of coding with the Power package, also really great. And then for someone had questions on structural equation models. So I actually just this morning added SimPower code to the example I'm going to do. And then I found a paper on latent profile analysis, but it gave me a headache. So the short answer is like, take people's best guesses, because otherwise I think you have to simulate it. All right, so let's do GPower. So I just stuck some pictures in here, but I actually have software. Okay, the question being, can you still see the software? Or are you only seeing the slides?
No, it's the software.
Okay, great. Just
Well, your email's also in the back.
I was like,
They're it all
I
out.
have 8,000 things open. Unfortunately, and I have talked to the guy who wrote GPower, you cannot make the font any larger. So I'm sorry in advance, because you can't make the screens any bigger. I have definitely emailed this, but GPower 4 is about to come out. I secret backhand know this because they're going to present hopefully at our computation and psych conference in the fall. I'm super pumped. So in the next couple months, the new version of GPower will also be out. But if you've never used it before, it's really great. It has, trying to move everybody's faces here. It has a bunch of different tests. I wanted to do the same one, but I recommend probably either t-tests or f-tests for the types of things that you might propose. Mostly f-tests, but if you end up having a t-test, you could do that as well. So I'm going to do f-tests. There are a bunch of different options. I find the way that they describe the ANOVA effects a little confusing, but I'm going to show you some resources that I have that will explain these like in depth, because I think it's confusing that they have like repeated measures within factors, repeated measures within, like that says the same thing twice, right? So a little bit of the nomenclature is a little weird. But we'll look at linear multiple regression, and you can do R-squared deviation from 0, meaning the whole model. I want to know if I can predict the entire thing at once. Or the other one that I really like to use is the linear multiple regression R-squared increase. So after controlling for X, can I find an increase based on this new predictor that I have? Okay. So I tend to use linear multiple regression because And then, because ANOVA and t-test are just a special type of an f-test. So everything is everything that we tend to do until you get into structural models and all that jazz, but like ANOVA's t-tests are all just simple, weird regressions. So if we kind of keep that in mind, regression actually power analysis wise can solve most of our problems. All right, so we want to pick a priori. There is this cool compromise effect option that allows you to kind of take that justify your alpha approach. They do have the post hoc achieved power, don't recommend, but then they have sensitivity as well. So if you know, like, the likelihood is that the sample size is going to be limited because I'm doing special populations, you might kind of calculate both. So I'm going to do a priori. And then let me close my little window here. But the main components you have to, this thing here is the effect size. Unfortunately, it's an F squared. Cohen got around, man. He wrote like all the effect sizes, right? So it's Cohen's F squared if you want, which is a different form of R squared. We don't tend to use it as much in social science, but I do see a lot of medical people using F squared. But I have the formula for you in my R studio here in the background, but it's R squared divided by 1 minus R squared. So you can convert, but if you're unsure, you can click determine and you can put in from correlation coefficient will allow you to put in R squared. And then there's other things that you can do from predictor correlations as well. So how many predictors are you going to have and all that kind of stuff. But I'm going to stick with the simple one. Okay. I put in 0.04. That's what I would consider a small to medium effect in regression in the field, the stuff that I tend to do. So I can calculate and transfer. For some reason, I guess 0.04 divided by 1 minus 0.04 gives me a very similar number, but sometimes it can be pretty different. Okay. And then in black font, for reasons I don't understand, it says alpha. Okay. So I'm gonna leave it as 0.05. Then power, and the default's 0.8, but let's move that up to 0.95 because we know that they might ask us for that. And then the number of predictors. So in this example, I'm using 3. Okay. And what that affects is the numerator degrees of freedom over here. So let me hit calculate. So the number of predictors affects the F test in the sense that it changes the numerator degrees of freedom. The sample size, the thing you're looking for, is the denominator degrees of freedom. Okay. And so it calculates what is the critical F value given this effect size, alpha, beta, and predictors. Okay. From there, it can tell you what the denominator has to be. Okay. So for a study with a small to medium effect and 3 predictors, we would need 400 people to achieve 95% power. Okay. Which, what'd you say?
You have a question in the chat here.
Okay. Sorry.
Katia asks, what are the predictors here? No interactions or 2 main plus an interaction, or does it matter what kind of predictors?
The nice thing here is that it doesn't matter because we're estimating the overall R squared value. So this is if any of the predictors, like as a whole for the model, are useful. There's a paper, it's not going to come to me right now, on like if you're going to do moderation, there's a paper on how to control for the correlation that you get when you have, you know, the 2 main effects and the moderator in the model at the same time. Obviously, those things are correlated because it's these 2 make up the moderation values. And it's a cool study that showed that most moderations are wildly underpowered because people don't account for this correlation. So if you have that kind of design, I can dig up this paper. But if you're specifically interested in only one of the predictors, I would actually switch to an R squared increase page, right? And estimate how much you think that predictor is going to add to the model. So the partial R squared, like how much is this one predictor adding to the model? So if you're going to do moderation, it's usually pretty low, so 0.01. Unless it's a perfect interaction, then it's high, but everything else is usually pretty low because the main effects take up most of the variance. Gosh, okay. So let's calculate the effect size. It's very small. Power. And this is where you could change. So you could say, I'm testing the moderator, but I have 3 total predictors where it's main effect 1, main effect 2, and moderation. Just in your example here. In that case, I would need 1,200 people. That's almost 1,300. I'm sorry, it's so tiny, to find the effect because I have to find it above and beyond. What else? If I change it to 0.04, it should give me, oof, no, not 0.4. Somebody would probably think you're cheating. All right. Yeah, it's down to 300 because I'm only interested in the one. But anytime you've decided to look at one of them, I usually tend to lower my estimate of the partial R squared because the correlation between predictors gets lumped into the other ones. So when you look at each predictor one at a time, it's only the amount that it's accounting for by itself and not the overlap as well. The overlap doesn't count. Okay, questions on G-Power. I think the hardest thing to know about the software is what goes in each box, personally. Kaya's making a face at me, though. Go
I
ahead.
didn't want to be on the camera, but I just want to say I just lost. You know, it's like I understand the main idea, but the problem is that like there are words. I understand the words, but I don't understand what they want from me. And like for example, total number of predictors, and that's why I ask you, and you explain this to me. But if I do it myself, I never know what to do because okay, number of predictors. What do you mean by that? Do you want 1, 2, 3, and like if you have resources, as you said, this would be great because it's just, for me, it's not clear what to do if I will choose another analysis.
Right. Yeah, let me hit those in a minute because I have a slide for them. But I know exactly what you're talking about. So I have some how-to guides. Not specific on G-Power, it's actually specific to the analysis type, but every one of them has a section on G-Power on how to apply like this specific design. Here's how I might click the buttons of G-Power. So perfect. I will come back to that. I have a slide for it. Even if my slides are possessed. Now I can make this bigger. So I kind of wrote a quick power example in R, but I thought for next week we might kind of walk through, like not have many slides and just walk through how to use FOE, which is Lisa DeBruyn's package on creating fake data, and how I would apply that to create a simulation. And so at the end, I might collect some more design ideas from you guys to talk about simulations. Okay, more in the chat. Oh, wonderful. Thank you, Savannah. So I'm using the Polymer Penguins library just to have some data. It just is not using mtcars or iris. It's data about penguins, and it makes me laugh. So the reason I picked the 3 predictor example is I actually have that as my model here in R. So LM stands for linear model. And this is the equation that I'm running, right? So I'm saying body mass is predicted by, body mass of penguins is predicted by their sex, their flipper length, and their bill length. Okay. And then let's see, is it predictive? Short answer is of course, because much easier to predict. Let me clear this out so it can be at the top of the screen real quick. There we go. So if I were to look at this output, I could say, okay, the overall F statistic, this is the component that you were normally putting into G-Power is the degrees of freedom. So the numerator degrees of freedom and the denominator degrees of freedom. So 3 here is tied to the number of predictors. It's technically 1, 2, 3, 4 minus 1. But as long as you can remember it's the number of predictors, that's how you would estimate what your numerator degrees of freedom are going to be. Okay. If you're doing a t-test, it's 2 minus 1, so it's always 1. Okay, and that's how t-tests are simple regressions and they reduce down. Okay. That's a very short version of that math, but that's why I tend to suggest people always use the power test I'm going to show you, is because it applies to so many of the common designs that we use, okay, for better or worse. So back to your question about mediation, moderation, right? Bill length probably makes a difference, but because its correlation with the other variables in the study is so high, it doesn't count. So that's one sort of issue. Its correlation with flipper length is pretty high, 0.62. That's one of the issues with testing a single predictor in the G-power way, is because if you don't know those intercorrelations, it's just going to kind of assume a partial, whatever partial R squared you have in it. And this is why simulation might be a better choice, because the intercorrelations between multiple predictors makes a difference. Okay. So flipper length didn't, or I'm sorry, bill length didn't get to count because flipper length took it all up. Okay. So one of the caveats to what I'm talking about. And I can find my multiple R squared. It's 0.81, which is totally ridiculous. And I wrote that out here, right, that it's ridiculous. In our studies, we wouldn't use that, but as an example, to get to F squared, it's R squared divided by 1 minus R squared. And so the F squared is 4, which is a crazy number. But let's just show you what that does to the power here. All right. So how many penguins did we actually need? Okay. So the function is power.f2 test. This will apply to anything that uses an F test. That F2 here stands for the effect size, but anything that t-tests and F can both be accommodated here. So regression, ANOVA, and t-tests. Your U and a t-test is 1. Okay. So there's a separate function, power.t.test, that allows you to take the traditional sort of T approach, but it basically calls this function underneath. So to simplify down, I would say use this one. Okay. So U here would be the number of predictors. So the number of predictors in the equation, if you have a t-test, it's 1. Okay. If you have an ANOVA and you have 1 IV, it's 1. If you have main effect interaction, it's 3. For the overall model, V, I don't know where V comes from, honestly. I don't know why they picked U and V, to be honest with you guys, but null. So whichever one you want to estimate, that's where you put in the null. Okay. So this is the number we're trying to get to. What is sample size? But what V actually stands for is denominator. So at the end, when you get the result, you actually need to say, okay, it's V plus K plus 1 to get the final number. Now G-power does that for you. If you'll notice, okay, it tells you the denominator degrees of freedom, and then it adds the number into it for the total sample size. Power does not. All right, run that code. It will spit out a number. I need 4 people plus U, so 3, 7, it's been a long morning, plus 1 for the intercept, so that's 8. Only needed 8 penguins, if the effect is truly this large. We change that to 95% power, I would need, I'm gonna round up, so 6 plus 4 is 10 penguins. And this is where you can kind of play around with. So let's say we go back to our original effect size, you should get the same answer. So 412, right, for overall. So let's go back. This is the regular model, right? 104 and 103 predictors, calculate 412, so 413 if I round up. So G-power is automatically rounding up. They're doing the same math. It just kind of depends on like if you want the code solution or the point and click solution. Whatever you do, include a picture or the code in the supplemental material, just because then is very clear what pieces you put in. And then by the time, hopefully your proposal gets accepted and you come down to the end, we can be like, okay, well, here's how I actually did this. Let's figure out how to scale that up. All right. So then I also did one with SimPower because I love SimPower so much. So I made up a very simple study in Lavaan. And if you have questions on the Lavaan code, I'm happy to answer them. But this is a simple scale with 4 questions on it, which is not very complicated. And I make some fake data with Lavaan. And just to show you, it'll allow you to run fake data. Sometimes the model's too perfect. Like it'll run your model to be like way too good, but it can give you the number that you need. So the hard part to me when doing structural models or network models or any of this stuff is knowing what the degrees of freedom should be, because the degrees of freedom are not tied to sample size. Okay, so when you get into the structural equation models, degrees of freedom is based on the number of parameters that you could estimate minus the number of parameters that you have estimated, right? And that has like literally 0 to do with the effect size. I'm sorry, not the effect size, the sample size. So I've always found this very hard because I want the sample size to matter. And it technically doesn't, in the sense that smaller sample sizes have more error. And so you will see models that are less stable, so to speak. But once you get past about 200, the issue more is about the model covariances. And so its power here is sort of removed, but the SimPower package has allows you to estimate based on effect size. I think the only 2 options here are RMC or RMSEA and CFI. I think you can also do compromised power analyses. I'm going to stick with a priori. I think it's either, no, they have other ones. So you'd have to look at their documentation. People love RMC and CFI so much. Those are like kind of most common to outcome measures that people use, especially, and they actually have a piece for measurement and variance as well. So SimPower does like the broad swath of different design types, but to keep it simple, let's say I want my RMC to be below 0.08 because the magic paper that says that 0.08 is great. And then I can set my alpha and my power here. I'll change this to 0.95. Degrees of freedom. The reason I show you a quick way to simulate is it's hard to maybe mentally calculate this number. So let's say the degrees of freedom is 2. P here is the number of parameters. So it's observed variables times observed plus 1. Okay. So we've got 4 questions times 4 plus 1 as our, plus 1 as our observed. All right, this is sort of SIM specific. So we actually have 20 possible parameters that we can estimate. And we're with degrees of freedom 2, we're estimating 18 of them. That is the hardest part here to me. And when I'm teaching students this stuff, we spend a lot of time talking about how do I estimate degrees of freedom, and I make them actually like draw it, and we always get it wrong. So I usually tend to say, okay, try estimating it on your own, then run it in your favorite software and see which one you forgot. Usually it's the required exogenous only correlations. There's a couple of spots you forget that it's going to estimate a number because it doesn't print it in the output. Okay. All right. The lovely part about the output is that it is pretty clear. So blah, 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 powered, simple, blah, 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 numbers, numbers, numbers. It tells you a number somewhere required in. There it is. Okay. So we would need 1,200 people for a small model. The bigger the model gets, actually, the more complex the model gets, weirdly enough, sometimes is what actually will make the numbers go down. Okay. So a quick and dirty way, but that would be total, right? So 1,200 people total. If we think about this being you know, a kind of a strict Ramsey. Our previous analysis for regression told us 400 people, right? And this total is 1,200 people total. Well, if I have 3 countries, that solves the problem at 400 people each. So that is total, not per group. All right, so then last but not least, and then we'll have time for questions. If I can get this to open. I found this paper that talks about detecting the number of classes. So how do I figure out the right number of classes? And I can throw this link in the chat here for you a second, but they've got this really fantastic table about, and what it looks like to me is it's based on the difference in the effect size for your predictors between classes. So like if you expect, you know, 3 classes and the effect size that actually differentiates those classes on whatever variable, let's say we're trying to predict depression profiles. If you think the depression differences between them is a 0.4 effect, Cohen's d, that's actually kind of where they put it in, because we talked last week about, like, I don't know how you would even know how many people, because you don't know what classes they're going into. But it seems like the answer is based on the size of the scales used to determine those classes and the effect size, the difference that you expect between classes. It's kind of, I think, where the manipulation piece comes in. And they have this lovely table that you can use as a way to kind of say, I would achieve, like, if we need 95% power and we know we have a 10-item scale, you can actually detect a Cohen's d of 0.2 between classes in a 4-class solution with 250 people. Does that make sense? Okay, you're nodding. Cool. So, you know, when you get into what you see happen as you move this way on the scale is, like, as the number of classes increases, power decreases fairly substantially. So they're basically showing that as long as you have less classes and more items, you get stronger power with less people. It's kind of my brief summary. The whole paper is great, but that table to me says, like, here's kind of where I can use this as a way to estimate what it should be without simulating the madness. Cool.
Okay, thank you.
Yeah.
Helps me a lot. Yeah.
Yeah, good. Because, like, I feel like it's so hard to conceptualize. And this is the direct link.
Oh,
Yeah.
thank you.
It's also open access, which, huzzah. Favorite world. Okay, quickly go back to the slides, talk about these resources. Can I get it to go back to present? Yeah. All right, so we've got these the slides will be uploaded after I fix whatever I did to them, and the code I already put online. Okay. So very briefly, what are these resources? So I have 2 links. I will say it is my own stuff. So I think the second one's probably better. Can I not click on it? Okay. Apologies. Where each of these pages has guidebooks that I put together for students. And so this particular one has it in 3 different softwares, but they also have, in the R one, it has examples of how to do this in Power, the R package. In the JASP one, I'm fairly sure it has examples on how to do this in GPower. So each folder has an overall set of slides, but then it also has what's the word I'm looking for here? These Word docs, and those are the files that you want to look at. So let me open one. They're all structured in a similar manner. I thankfully had a student helping me with this at the time, where it's a complete walkthrough. So it gives you an example of what all the terminology is. Back to Katya's question, it gives you the data sets are there, but then it also has the like OpenGPower, here's the test we're gonna do, here's why we're using that test. So this kind of thing, I think, is what you're looking for? Question mark, yeah. And then it has a picture of it. This is an old version of GPower, but it has a picture of like that data actually entered. And then it presents the results right up and the actual output with highlighting for each one. So it has like, how would I do the analysis from start to finish on a silly example about the number of books that you read for class and then attendance in class. Does that predict your final grade? I mean, all the examples are sort of silly, but it does have like, how do I do power? How do I do data screening? So if you aren't sure what the steps are for data screening for your analysis, you can pick that up too. And I have it for a lot of different designs, not a whole lot for SIM, but you could look at the EFA one that would correlate. And then if you want to take the R route, it has the same type of outputs. So for example, gosh, and it breaks it down by type. So this would be a between subjects one-way ANOVA. I spent so much time writing these. If somebody wants to open them, oh, it actually still has GPower in here as well. But I also included the link to my more recent class. So I haven't taught this class in a while. It was at my previous institution. But one of the other ones has the information with, definitely has power in it because I'm teaching it right now. And it links you to this one. And so you can look at R or R flipped, and it will have the power code in the slides in markdown format. So that's the other link on there. Okay. And then just as an aside, as a mild self-promotion, you can actually take my entire class. So it actually also has links to the videos in order. If you're ever wanting to take SIM, a lot of people will watch the whole class. I think it's crazy, but free open source materials. Or if you are like, get stuck teaching a class that you are like, I don't even know where to start, feel free. All right, last but not least. So for next week, my thought was that maybe we could do a quick and dirty simulation with Faux, because I didn't think I could make it all fit today. Clearly not. I will let people fight over that in a minute. But then I have been told also after the 2 weeks after that are open for chat times. So we won't actually have this time on the 12th because I'll be on a train. But this is where people will send out like a kind of a when to hang out, and you can schedule a time to just like specifically talk about what you want to do and what we can do to make that proposal happen. So we can go over your specific details and where you need the most help. Like if you need the help on the analyses or the power or design or scaling up or like whatever you want. And we've obviously seen same faces over and over again, so we'll send that to you guys first to pick. And then I'm required to show you this slide every week. All right, so Savannah, if you want to hit stop, I will put the links to those two OS pages in the chat. Oh, Savannah will do it for me.